So we've been asked by a couple of customers just to discuss biofilm and biofouling, especially when it comes to food and beverage, pharmaceutical, makeup, cosmetics sort of applications, more specifically to do with distribution of water and biofilm accumulating in pipework and filter housings. So we're going to go through a couple of things that we use as our first stop of biofouling, or how to reduce the possibility of biofouling. So let's have a quick conversation about what biofouling is and where it's most likely to occur in water distribution or even food distribution pipework. So if we have a look at a pipe cross section. So a normal pipe will be, you have your water flow going through, and it will go through the pipe, and hopefully your water is clean enough and you won't pick up deposits of biological matter. But doesn't matter how clean your water is, bacteria and broken down bits of organics will eventually end up in your pipe network system. And what happens is, if you zoomed in on the pipe surface, you'll have natural indents and mountains and peaks, and they call that roughness, or it might be a KR factor depending on which pipe supplier gives you the specification. So you can absolutely start looking at your pipe selection, which is step one, selection of pipe, how this surface roughness is dealt with. But why is surface roughness so important to myself or anyone else that is a system designing a system? What happens is you'll eventually accumulate in these peaks and troughs, and these are microns thick. These are micron discrepancy of the roughness of your pipe. You'll actually find that you'll get biological matter building up on the surface of your pipe, and it's these peaks and troughs where they accumulate. So what happens is eventually these will get big and they can start spanning the whole of your pipe surface. And in here, it's like a slime, a biological slime. That's a living organism now. And we get something called sloughing. So little parts of these will start breaking up and they'll come loose in your water, and then they will get picked up. When it gets to that point that you're getting this sloughing of biological fouling coming across, you've lost your system. You've lost all your network system. You now need a deep sanitization to actively remove. Now, this is what happens when you've got no mechanical design controls, or you've not got any system process controls, i.e. sanitization. So what can we do to try and help remove or reduce biological? So we're going to go back to the pipe. This is your pipe. You've got water flow going through your pipe. The first stage that we should do is turbulent water. So we've got a pipe. If we run that pipe meters per second, if we fall below a certain number, so let's say below 1 meter a second of water flow passing through there, then that might not be enough to get what we want, which is turbulent flow. So if you imagine water below a certain velocity through your pipe, you'll get something called laminar flow. And laminar flow water looks very nice on a fountain, but laminar flow doesn't create any disturbances. It's very nice and it flows through the pipe, but it doesn't swirl around. It doesn't give us any mechanical shear forces that we want. So I'm going to rub this off again. Once we start moving up and we've got a pipe and we start pushing that water through at higher velocities, we then get something called turbulent flow. And the water is going to come through your pipe like this, and it's going to be all messy, and it's going to create an environment that is going to be very difficult for biological matter to start accumulating in these peaks and troughs. And you physically don't allow any biological matter to start building up. So this is assuming that we've got biological microorganisms within the water. So we will use, this is our first line of defense, high turbulent flow. There is a downside to that. You can create unnecessary wear within your pipe. So really we look to something called a Reynolds number. And we will use that typically in food and beverage, pharmaceutical. You want a Reynolds number which is, I think, above 3,000, 4,000. The higher the Reynolds number, the better. But it's the velocity of water going through your pipe, so meters per second. If you can get that above 2 meters per second through the whole of your network, you most likely be hitting the correct Reynolds number, and you're going to be getting that good velocity to produce turbulent flow to stop all this. So then the next one, so that's the first stage, and it's really easy to implement. So you've got material selection. If you want your pipe, if it was hygienic, you go for a stainless steel. You can then get higher grades of stainless steel. You can get higher specialities of the internal surface smoothness of your pipe, if you will. Then the next one is how fast are we going to pump the liquid around to create that turbulent flow. And then you look at the wider network system. So if I was to draw a quick P&ID, so we've got our nice treated water that Hydra-Clear have treated up super duper spec. But now on your network, you just pump it directly out to a valve, let's say. What we've got there is the perfect breeding ground because it's a dead leg. It's now stagnant water. I mean, you could argue and say, well, you know, we open that valve and it cycles and it fills an IBC, and we do that periodically every 2-3 hours. But we only do that Mondays to Friday. At the weekend, it's just sat there. Nice hot summer's day, we're now cooking that water. So although Hydra-Clear have given you the best quality water whatsoever, you don't use it over a weekend. And from the atmosphere, we've now got biological matter entering your treated water tank. It's now going to sit over the weekend, 72 hours. It's nice, hot factory. We're going to end up with biofilm fairly quickly in that. So a simple thing to do. We still want to fill our tank. We still want that tank to be filled, and it's still only going to operate and fill that tank Monday to Friday. But I'm going to take off and return back to my tank. And now I've got a looped system. So I'm going to keep that water flowing at that turbulent flow rate all the time, 24 hours a day. And what that's going to do is allow this not to be utilized, but make sure that we don't have any dead legs. And ideally, if you've got multiple user points, you'll have one ring main, and you will just add on the user points to that ring main that you need. And then the ring main will be flowing at the correct velocity, and then your takeoff points, hopefully you have them hygienically installed by following good practices. Your valves will be installed as close as possible to your ring main. So this is step number 3. We've now got a ring main loop control. That's going to be a very good mechanical and simple way of keeping the velocity moving at all times. And then we can look at other stuff. So you might put a filter housing in there and say, you know, that's 0.2 micron filter housing. That's going to create your physical stop. So now we've got the flow rate, we've got the metal, we've got the hygienic stainless pipe, which is really good. It's a nice, smooth internal finish. We've got the velocity going round, and now we're going to filter it down to 0.2. So all we've done there by adding mechanical and thinking about this at the design process, or even assessing your existing system, all we've done is mechanical. We're not adding chemicals. We're not having to change procedures and making sure that you're doing this. This is just basic mechanical stuff that will not eliminate, but will reduce the possibility of you getting biofilm throughout your system. And then once you've dealt with the easy stuff, this is what I call easy stuff. If you're having a new system put in, this is what we would recommend putting in, just as the first stage. And then you would look at your operating procedures. So some people on some sites, they might say, well, we will take a sample of this periodically, and then we'll check it for micros. And if it's above a certain point, then we'll start doing CRPs, or you might not. That is completely up to the customer. But one thing that I did want to mention about the filter housings and the importance of filters. So once you've got all this in place, everybody says, well, I don't need to change my filters until I start blocking up, which is possibly correct. In fact, scratch that. I don't want that going in the video. Yeah. So edit that if you can, and then I'll carry on. Right, okay. So we've got the velocity going back through into the tank. Everything's so good. And then we have a look at the tank itself. So hopefully the tank is of a suitable grade. If you speak to Hydra-Clear, it will be. Hopefully the tank is of suitable grade, but we've got a body of water in there. The next thing that I would look to do, it's what we would look to do, is we've got a body of water. It's now being pumped around at the correct velocity, but that tank is 100,000 litres. The correct velocity is only 2 meters cubed an hour. Well, that's not going to work, because I think that could still be classed as a body of stagnant water, because your pump is only 2 meters cubed an hour and you've got 100 meters cubed. Well, in one day you're only going to turn that tank over half. What we like to do is turn over that tank of water by passing it through, especially on the filter as well. If we can turn that body of water over 6, 7, 8, as many times as possible, obviously it's got to be within budget, as many times as possible, that then the tank isn't a stagnant water body of water. So we would size your pump and your ring main to ensure that we can turn that tank over as many times as possible. What is that doing? Well, anything that comes in from the air, any biological matter that will come in through a normally aspirated tank, is going to get captured at the 0.2. But then, more importantly, on the inlet, we'll probably install a spray ball. So then what we've got a spinning spray ball that, again, sprays water across all the sides of the tank, so we're not getting dry spots, and we're not getting a slow up and down movement of the tank. We're spraying water in to try and get the same agitation that we've got in our ring main. You want turbulent water. You don't want any water just sat nice and moving smoothly up and down the side of your tank, just the same as you don't want it in your pipework. So we'll put a spray ball, we'll agitate it, we'll run the pump higher. So again, you want a minimum of 24 hours. That tank needs to be turned over a minimum of once per 24 hours. The higher the number, the better, because it's moving up and down. We've got a spray ball at the top, so it's agitating the sides of the tank, and you're not getting dry spots and wet spots. And that is mechanical biofilm. And this should really be done on the design. But if your system is struggling with biofilm fouling, absolutely call us in. We'll come and appraise the system from a mechanical and maybe a procedural point as well, because sometimes we go to customer sites, they're not doing any spot checks, or they're not doing regular sampling for biofilm, and then, unfortunately, we've been to a couple of customer sites, they've had bad product, and we've gone in, and it's been a journey of us working together just to come up with the best system. You've got to bear in mind that some of the systems that we go to, they've just been added to and amended over many, many, many years of them being in production service. And it probably might get to the point where you can't really call it an optimum system for reduction of biofouling.